Thank you very much. Thanks, Kirill, for inviting me, and it's my pleasure to be here, back here again. So today what I would do is that, because the audience is very small, so do not hesitate to raise your hand, and the good thing is that we have a fantastic whiteboard where we can actually write down something and we can discuss more details if you need. So some of you may have heard my talk before, but those of you who haven't, so the title of the talk is Towards Asymptotic Freedom for Gravity. So this I have been working on with some of my colleagues, especially with Warren Siegel and Tirthabir Biswas, who has been working with me for a while on this topic, and then we have quite a number of students, postdocs and senior fellows who are working with me: Alex Kolosev, Sergei Vernov, Eric Garvik, Tomi Kovistov, Andrew and Spiridon. They are my two grad students. Okay, so let me plan the talk. So what I would do is that I would just give you a brief motivation. What is the whole purpose of extending gravity and talking about some aspects of the gravity, which is about the ultraviolet aspects of gravity? Why do we want to talk about them? So as soon as we talk about the high derivative gravity, we are actually slightly motivated towards discussing essentially gravity, because gravity, as you know, that you have normal, it's just two derivative theory, but as soon as you go for making some corrections, say one loop corrections or two loop corrections, you automatically incur more and more higher derivatives. So in gravity, the higher derivatives are very common, and if they are higher derivatives, you immediately come across a problem which is usually known as ghost. So the question is, how do you really tackle this ghost problem in higher derivative theories of gravity? So that's the second part, which I will discuss in some details. And then what I would do is that I would give you a covariant generalization of this, whatever I'm doing, generalization of high derivative theory of gravity. So nowhere I would essentially break my gauge invariance. I will maintain my gauge invariance. So that's the one of the sacred thing about this plan. And towards the end, I would give you some applications. One application would be essentially to discuss in the context of time-dependent context, like in the context of cosmology. And another application which I will discuss would be about black holes. And if time permits me, I will discuss a little bit about what are the ways one can actually go and say more about background independent aspects. But that's a little bit very much in the work in progress. So whatever I'm going to tell towards the end would be more like a conjecture rather than making a statement. Okay, so as you all know that when it comes to gravity, whether it's just the classical gravity, whether it's Newtonian gravity or Einsteinian gravity, the problem in gravity is the UV. In the UV, the theory becomes pathological. So as you can see from the Newtonian potential, 1 over r potential. So as r goes to infinity, the potential is very well behaved, but as r tends to 0, you naturally get all sorts of problems. So this problem actually remains there not only in Newtonian gravity, but also in Einstein's gravity. Now, of course, there are various ways of attacking this problem, and whether it's loop quantum gravity or string theory, and in particular, string theory, I'm not an expert in loop quantum gravity or other versions of quantum gravity, but what I have understood from string theory side is that string theory is inherently non-local. Now, if the action itself has some non-locality built in, then there is a hope that maybe there is a way that you can tame some of the short distance behavior. Short distance infinities, the divergences, maybe you can tame them. Or maybe, if in reality, you would be able to resolve them completely. So that's the hope we have as far as the string theory is concerned.
Are you referring to the extendedness of strings?
Exactly. Essentially, because string, I will come down to the next slide, that why string theory has this kind of behavior. But before I go on, there are motivations. Of course, there are physical motivations. We want to proceed the problem. Without motivation, there is not, doesn't really make sense. So a couple of motivation which comes to my mind is, one of the things is the resolution of the singularities, essentially black hole type singularities or cosmological singularities. So essentially the resolution of singularities is one of the key thing to, which essentially when one of the goals of string theory has been to resolve some of these issues. But as you would see that even though you want to remove these singularities, there are other issues which prop in whenever you try to do that, and that is so these two problems come hand in hand essentially. And the other aspect is about marrying between quantum mechanics and gravity. And as soon as we marry these two fields, we have this problem of say for instance black hole information loss paradox and things like that. What can you say about this? Although I'm going to say everything classically, today I'm not going to touch anything about the quantum aspects, but nevertheless you would see that you would get some hint about there could be some hint about resolution of even the information loss paradox connected to your black holes or Hawking's information loss paradox, and we'll get a chance to discuss about it a little bit later. Now I would like to modify, or anybody would like to modify any of these things, make it slightly better while keeping the IR infrared property of gravity. You do not want to tinker with the infrared property because it's very well behaved. Of course, there are people try to add massive mass term in the gravity and things like that to modify the infrared aspects. But for the purpose of the talk, I will not modify the infrared part of the gravity. I'll keep the infrared part as 1 over r, and we'll just simply try to concentrate on the UV aspects of the gravity. So that's the motivation. Now, I hope that, I wish I were a kind of like a magician with a stroke of genius like what Einstein had done, could have given you some very nice actions. And one of the action could be, these are the two kind of action which I could present you in a very simple way. But, so what my aim would be to essentially to tackle the first part of the action. So those of you who, would like to switch off a little bit, you can switch off, but at the end of the day I would like to show you that the first half of the action, essentially the first action, how I come about to this action and what properties does this action have towards understanding of some aspects of singularities in black hole and in cosmological sense. And the second part of the action would be more like a conjecture, which still I have not proven it, or I have not shown it by any stretch of my imagination yet, but that's something which we are working on in future. Okay, so coming back to some simple facts which many of you know, and as you have raised, that why the strings help us in this respect. Now strings, essentially you are not playing with one parameter, you have essentially two parameters. One is the string coupling constant, which is GS, and the other is the size of the string, the alpha prime. Now in principle you can write down an action taking into account of the string coupling corrections. So one loops G string, two loops G string, and you can also do write down an action by taking into account of the alpha prime corrections. So the alpha prime correction essentially tells you the width of how the string itself is wiggling around in your space time. So there are two fundamental constants in string theory, two parameters which you can play around. Now the fact that the strings have certain width tells you that the interactions, essentially the two strings interact, is basically non-local. It's not a point-like interaction, and as a result of that, what you get is something very interesting, which of course was known way back from the days of Dirac and Born-Enfield, that you could write down a Dirac-Born-Enfield action, and that action comes out quite naturally also when you do to all orders in alpha prime correction, like as this action, for a finite G string. So it's a kind of like, you can think of as one loop in G string, but to all orders in alpha prime correction. Now, as I said, that way back in the days of when Dirac and Enfield was Born and Enfield were trying to resolve this problem in quantum electrodynamics, that you take a point charge particle, you try to calculate the self energy in Colombian electrodynamics, it would give you infinite answer when you calculate the self energy of an electron. But with this action, is a similar kind of action, much simplified action. You can write it down for the Dirac and Born field, which they have written down, and you compute the same self-energy of an electron, you would get a finite answer. So this is what happens, comes quite interestingly from the string theory. But you have to keep this in mind, that this action is actually comes from the open strings. It doesn't come from the closed string. So the challenge for any string theories would be to, can you really capture a similar kind of action where, in the closed string sector, where you only have gravity, where you take into account of all alpha prime corrections. So somehow, well, it's a very challenging problem, and still we do not have an analog action like this for the closed string sector. So that's the problem, the challenge we have right now. Now, let's go back to a little bit of what we know about perturbative quantum gravity. Now, even in perturbative quantum gravity, many things are known, and many people have worked into it. This is a very old subject. Way back in 50s and 60s and 70s, there are many classic papers were written down, and the kind of the things which I'm going to tell you perhaps was very well described in this famous paper by Toft and Weltman's paper. Now, so if you want to compute just one loop, just pure gravity, forget the matter part. So you switch off the matter part here, just concentrate on pure gravity. Then what you can, of course, when you are taking into account one loop correction, you would expect that you would get invariant terms such as r square, r mu nu square, r mu nu lambda sigma square. So these are the three kind of corrections which you would get when you do a one loop computation. Now, in this very classic paper by Toft and Weltman, they actually computed these coefficients, alpha, beta, and gamma. And one particular choice will give you actually some, as people know about, many people who have worked here, is the Gauss-Bonnet gravity. The Gauss-Bonnet gravity has exactly this kind of combination, 1 minus 4, 1. But in reality, I mean, when you do the real one-loop computation, it's not like Gauss-Bonnet gravity, but this alpha, beta, and gamma, these are some numbers which has been computed very accurately for one loop. People also know, in fact, in the seminal paper by Toft and Weltman, they also claimed, they have shown that if you go for two loops, you just have to add only one counter term. So it becomes like a scalar tensor theory at the end of the day when you add this counter term. But going from one loop to two loop and beyond two loop, things become much more complicated, because the number of diagrams, number of Feynman diagrams keeps increasing by number of loops. As you increase number of loops, the number of divergence, the number of diagrams itself become infinitely large, and computing for each and every diagram or computing the counter terms becomes a nightmare. And if you just do normal, very simple, just write down the superficial degree of divergence, say for instance here I have written down in terms of d, it keeps increases as the number of loops increases. So this perturbative aspects of quantum gravity becomes a nightmare if you go for beyond, say, 2 loops, 3 loops. It becomes nightmare to compute the diagram, because the number of diagrams, they keep increasing so rapidly. But anyway, so these are some basic things which we all know about some aspects of quantum gravity. But there was another interesting revolution which happened way back in 70s. Well, it was quite well known way back in 60s by Uchiyama and David. In 1961, they had a fantastic paper where they had kind of like conjectured that fourth derivative gravity, essentially the same gravity as I discussed, because r mu nu square and r square and r mu nu lambda sigma square, there are 4 derivatives. So 4 derivative gravity can actually suppress the ultraviolet behavior. And the way it suppresses is precisely because if there are 4 derivatives, so when you take into account of the propagator, it will have at least 1 over k to the power 4, the leading order term, where k is essentially the momentum. Okay? So that was the whole idea of Uchiyama and David, and it was well proven by Kelly-Stell in 1970s paper, 1977, that the 4 derivative gravity is indeed renormalizable theory. So as you know that gravity is a gauge theory, so it behaves exactly like your non-abelian gauge theory. In order to write down, once you have written down this action, on top of that you have to write down the Gauss terms and anti-Gauss terms, and you have to, I mean, at the end of the day, when you look at the total action, it is a little bit more complicated than the simple action which I have written down, because I have not written any of the Gauss terms or anti-Gauss terms and the gauge fixing terms and things like that. But when you do the entire procedure, you indeed find that the propagator goes as 1 over k to the power 4, and 1 over k to the power 4 times d4k actually ameliorates the behavior as compared to d4k times 1 over k square. Yeah.
Is there a reason for not extending the minimum square?
No, it's, r square is there, r mu square is there. You should also get r mu lambda sigma square. The y term should also be there. Yeah. So I think I missed. I've not written down, but it should be there. In principle, as you said, that you can also eliminate by the total derivative. Exactly. Good. So one of the classic result of Kelly's paper was that yes. So the lesson which we have learned is that indeed you can soften the UV behavior by adding extra terms in your action. So essentially, as you add more and more terms in your action, you have to keep in mind that gravity is a gauge theory. You cannot write down arbitrary mass terms and things like that. So all the corrections which you get, these are kinetic corrections in your kinetic terms, like r square, r mu square, r mu lambda sigma squares, and things like that. So when you do that, you immediately realize that yes, you can ameliorate the propagator. Sorry, you can ameliorate the UV aspects of the any diagram, but immediately you have to modify the propagator. Your propagator is no longer your GR propagator. The GR propagator, perhaps those who recall it, it would look like your, if I write down pi, it would have the tensorial component and the scalar component, and it has this behavior, 1 over k square divided by minus 1 over 2k square in 4 dimensions, okay? And why it comes with minus sign is also very beautiful because I will tell you a little bit maybe in the next slide. So this is the pure GR propagator for pure Einstein's gravity. So this is your GR propagator, okay? Now, as soon as you modify your gravity, you change the nature of the propagator, you add more terms, there are more degrees of freedom. So as soon as you have more degrees of freedom, essentially what you are saying is that there is extra degree of freedom which is propagating in your space-time. It's no longer the massless graviton which is propagating like as in the case of GR, it's just purely the massless graviton. But on top of that, you have extra degree of freedom which is propagating, and that degree of freedom can actually harbor something bad. And that's what happens in this kind of gravity, in spite of the fact it is renormalizable. What he found, in fact, Kelly himself, found in his paper that it has a ghost. This extra degree of freedom has a negative norm. So one way to see is that the residue goes negative, this minus sign, which you see in your propagator.
Negative minus sign from the second term in pure GR propagator.
Yeah, but this is it's a very good point. This is a benign ghost. And it's a very good point which you have mentioned. It's a benign ghost, but these ghosts are actually malign ghosts in a sense. It really is about. This is a benign ghost. I'll come back again perhaps in the next slide. Why this ghost, why this negative term is important for pure GR. And it's a very beautiful concept, which I'm sure many know this about this fact. So the challenge for us is that, yes, you want to modify gravity, you want to add perhaps extra terms, but you also want to get rid of this extra degree of freedom which is propagating. So that's the thing which you need to tame. So let's see how can we tame that. So that's the challenge we have, and let's see how can we what can we do with that. Now the ghosts. Now you don't have to really go to the gravity to understand the behavior of the ghosts. Let's take a very simple even scalar field theory. Because you could see the gravity as such behaves almost like a scalar, because gravity has these two components. One is the tensorial component, other is purely the scalar component. And you see that this part has this negative sign, as Kirill mentioned. And this part is fine. The tensorial component, the spin 2 part is fine. The spin 0 part has this negative term. So let's go back to a very simple action, very simple higher derivative action for the scalar field. So let's consider this is the simple example which one can think of. In principle, you can generalize that to many terms. In principle, you can have box square m1 square, box plus m2 square, and so on and so forth. You can write down as many terms as possible. But just for the sake of illustration, you can play with only these two terms and see how it comes out. Now, when you invert when you write down the propagator, essentially invert your equation of motion, what you find is this term 1 over p square times p square plus m square. Now, as soon as you have two distinct masses, here one of the mass is 0 and the other is say m square, other is m. So as soon as you have two distinct masses, you would immediately realize that your one of your residue will be negative, and as soon as the residue becomes negative, you immediately see that there is a ghost in the problem. Okay, so that's one way to check the ghost. Other way of checking the ghost is doing explicit computation, and by redefining your action, you can see the kinetic term itself becomes negative. So that's another way you can do it.
There must be another way to phrase it. This is
Yeah.
why I derivative theory.
Absolutely.
Absolutely.
Absolutely. Absolutely. So what ghost means is that your vacuum is no longer stable. If your vacuum is no longer stable, it means that when you do any quantum mechanical process, the vacuum itself can decay into lower vacuum, and lower vacuum there is no minima. Gravity doesn't have any particular stabilizers, a particular minimum. So the state becomes no longer stable anymore. So the lesson what we learn is that the ghost can, even for the scalar field theory, if it has only the derivative interaction so far, it cannot be cured just by taking order by order. Okay, you need perhaps it gives you some kind of like hint that no, I cannot do it in just I cannot curtail my action up to this order. Maybe I have to take into account of all orders taking into account, and that's the kind of like lesson we have learned from very simple example. Okay, now coming back to the graviton propagator and why there is this negative sign. Now perhaps those of you who know, who have done a little bit of GR, you would realize immediately that gravity has essentially 2 degrees of freedom which propagates. One is that it's a transverse traceless. Yeah. So essentially, when you look at the gravity waves, which many of the undergraduate studies you do X and Y, so there are 2 particular waves which you study. This kind of motion, or you have this kind of motion. Yeah. So these are the 2 degrees of freedom essentially which propagate. Okay, in your space-time. So the question is, why only 2 degrees of freedom? After all, gravity is it has a tensorial structure. Yeah. So if it has a tensorial structure, given a tensor, given a metric, I can write down the same metric in terms of scalar, in terms of vector, in terms of tensor. So why only the tensor and the scalar degree of freedom which propagates in your normal GR? What happens to the vector degree of freedom? Now that's the beauty. It's like your Higgs mechanism. The vector degree of freedom gets eaten, becomes very massive. For any particular momentum, it gets decoupled essentially. It becomes so massive that it does not even propagate. But in order to do that, you require this negative sign. So this is, in this respect, this is really a benign ghost. It is there in your propagator, but it is there for a good purpose, that it makes essentially the vector degrees of freedom very, very heavy. So essentially at the low energies, what propagates is only the spin 2 part and the spin 0 part, the scalar component and the tensor component. And these are the... Okay. Well, of course, I mean, you need to, in order to do this, in order to write down the propagator itself, you need to gauge fix. Otherwise, I cannot do it without gauge fixing. I need to fix my gauge. Okay, so that's true. So that's a very, absolutely. What you're saying is absolutely correct. It's the gauge fixing which really fixes this. But even there, I mean, the physical picture is that the vector part doesn't really appear. Now vector, of course, in the mathematics, when we do mathematically, the vector part doesn't appear because you use a certain projection operator.
Contains everybody except the scalar. It contains vector parts as well.
No, okay, so that's the thing. Okay, so one way to understand that essentially you have 2 degrees of freedom which propagates. Okay, and one way to, mathematically what you can do, which I think as you're telling me, that you have some projection operator, you project certain degrees of freedom, and at the end of the day, perhaps you recall that in the projection operator you have, essentially there are 6 operators. The scalar component, the vector component, tensorial component, and scalar and I think among the scalars they mix. There are these projection operators, I think you know. So when you do that mathematically, of course, you get the structure, but the vector component never appears. It comes out very smoothly. But physically, one way to understand that vector component becomes essentially decoupled. One way to understand it. Of course, it's, I mean, that's one way to essentially express what you're saying is absolutely correct. Is because of the gauge invariance, it doesn't really appear. It's in a way, it's like a Higgsing mechanism, that one of the degree of the photon initially is massive, but well, you can have massive and massless degrees of freedom for both, but the massive degree is being eaten away. So in a kind of like a very, I mean, simple way, I'm saying that it's kind of like a Higgs mechanism. But anyway, we can discuss about this. Okay, so as Kirill pointed out, that you have to do this computation in a particular gauge, and as soon as you do it in a particular gauge, you can actually do it for any arbitrary d dimensions. So for 4 dimensions, you are left with 1/2 in the scalar part here. Okay. Okay. So these are the things which we know, so these are things which we have to keep in mind, because if I want to modify my gravity, at the end of the day, I would also like to recover my infrared gravity, because infrared gravity is very well behaved. I have seen it, I mean, many of the experiments I have seen that infrared gravity is well behaved, so I need to capture that no matter what happens. But the question is, what kind of terms would you like to add on top of R? Now, as soon as you think about writing R corrections, you cannot write down arbitrary terms. So what you can write down is there's something like this, where these dots could be your, you know, any number of essentially mu, nu, lambda, sigmas, but this O could be your operator. So these are gauge invariant terms which you can in principle write it down. These operators, of course, a priori you do not know, other than the fact that this is a total, this expression is a gauge invariant quantity, this expression is a gauge invariant quantity, and so on and so forth. So in principle, in gravity, that's the problem. Just because we don't have the full theory of, you know, quantum gravity, no one stops me at only 3rd order or 4th order. In principle, I can go to all infinite orders. But that's a really hard task. And also, for many good purposes, it's not very useful, because if you want to understand some simple question such as, you know, like propagator, the concept of propagator is very well defined around the Minkowski space. So some of the things which you want to, I mean, you know, the 0th level questions, 0th level answers, if you want, you can actually think of keeping it up to invariant under order h square, because if you perturb it around your Minkowski background, the R term becomes of order h. So h mu nu is your perturbation. So this is, but even up to this h square correction, there are many terms you would see. So in principle, you can write down, this is a gauge invariant operator, O, and contract it with, you know, with appropriate indices. So the fact that you do not know this operator itself causes a big problem. And in principle, you can write down many possible terms. So if you really expand this action, you would see that there are total 17 or 18 terms you will get. So in principle, what I have done here, so what, I mean, at the lowest order, you have this R, then you can write down box del mu R, and then similarly you can write down del mu square R, and so on and so forth. Similarly for R mu nu you can do that, and similarly for your Y term R mu nu lambda sigma you can do that. So these are essentially your gauge invariant. These are you close the essentially the algebra by taking proper indices correctly. Of the Riemann square. But still there are many terms, something like there are 14 terms, 14 or 15 terms here you get on top of your R, so maybe total 15 terms. And on top of that, these functions which I have written down, they are,
Which of them are total derivatives?
so essentially, oh yeah, that's a good point. So it will reduce. You are absolutely correct. Many of the terms are redundant actually, and you will see a very simple reduction at the end of the day. So which is there in my next page. So these functions, f's are, again these are unknown functions of boxes, and there are infinite of them. So each and every term contains infinities. But as I said that, and as Kirill pointed out, that, you know, okay, you are saying that you want to do something with gravity, but there are infinite terms, so what do you gain at this point? At this level, we don't gain much. You need to simplify the action, and the simplification happens very naturally as many of the terms becomes, you know, they come as a total derivative, so you can discard them properly. So that's the point here which essentially Kirill mentioned.
Do you allow for non-local terms as well?
So these are, the non-local terms are always there. Higher derivative means that there are more derivatives. and more derivative means individually they are non-local.
You could have, like, in these functional box, you could have inverse box.
Oh, no. I want to play with only functions which are linear in boxes. Sorry, not inverse function, only analytic functions, not 1 over boxes essentially. I want to play with only the analytic functions so far. So many of the terms are redundant here, and at the end of the day, exactly the same configuration you get as you would expect anyway in one loop, proportional to R square terms, R mu square terms, and R mu lambda sigma square term. Okay. So again, just to I'm just what I'm showing is that it's kind of very similar structure like Gauss-Bonnet because it's very simple to write down, but in reality, people have computed these coefficients for one loop, alpha, beta, gamma, correctly. But one thing to notice that in sure, yeah, yes, in the Minkowski space, even that term will go away. Even that term will go away at the end of the day. You're absolutely correct. But I just kept it just to show the similarity between these two. So. Okay, so one thing to notice that in usual when you do not do this higher derivative expansion, these coefficients alpha, beta, gamma are just constant numbers. But now you can think of these alpha, beta, gammas are now some function of boxes, and box means when you go into the Fourier space, these are functions of some momentum. So essentially these are now, you can think of in a very loose sense that these are being dressed by some momentum dependent terms in that action. So f of box, f2 box, f3 box, and they all contain these infinite derivatives. Sure. That's good, yeah. Yeah.
Because if you don't truncate this action to just quadratical Riemann, if you know all possible Riemann, then you can also start playing with field definitions. You can shift the metric, like for example, power of Riemann or derivative of power of Riemann, and then you can achieve further simplifications by doing field definitions. You cannot do these field definitions if you truncate the Riemann squared order, because then you destroy the Riemann squared order nature of the Lagrangian. If you think about that as just part of the bigger Lagrangian, then you can many other simplifications are possible. So I
sure.
All of these terms can be removed by
But you would see that not all of them, but to some extent you can remove the last one, but you would see that the R square term, R mu square, you have to keep at least. And we'll see that in the next slide. Okay, so once you are given this action, suppose you take this action, and then you ask the question, okay, around the Minkowski space, how this action linearizes, because that's the simplest order, zeroth order question which you can ask to understand the nature of propagator and things like that. So that's what we have done. We have just taken this action, we have perturbed it around your eta mu nu, and after after doing this exercise, your action looks like h in terms of h mu nu's now, equation number 3. Now, as Kirill pointed out, there's a beautiful relationship which emerges automatically, and it is also, it happens because essentially you have inbuilt Bianchi identity which is built in. So energy momentum tensor is always conserved, and that helps you to understand this point. Now these terms, like now f1, f2, f3s can be recast in terms these new definitions, which is A of box, B of box, C, D, and F. Okay. Once I have linearized that action, the top action I have linearized, I have written down in terms of 3, and now you get in terms of A, B, C, D, F. And A, B, C, D, F now can be rewritten in terms of these functions, original functions, F1, F2, F3s. Okay. But just by looking at these 4 A, B, C, D, F, which are function of boxes again, you immediately realize that there's something very interesting thing happens. That A plus B cancels out immediately. Term by term they cancel out. Similarly, C plus D, term by term cancels out. And similarly, B plus C plus F, term by term they cancel out. So at the end of the day, you can actually switch off F completely. And as you can see that even that action has one redundancy which I can get rid of it. So you can left with essentially the R, F1 box R mu nu, F2 box R mu nu. So this term you can switch it off, at least in the Minkowski space, you can do that. Sure. Okay, so you can choose F equals to 0. So you can switch f. You can take f equals to 0, and still you would satisfy all the equations. That's what it means, and that's what also turns out to be true if you do this. Another very simple exercise is by looking at. So what you do is that you take this action, the action which I showed you initially, and suppose if there is a point-like source. So you write down the equation of motion for that point-like source, and that point-like source is essentially your kappa times tau mu nu, okay? And you impose the Bianchi identity, essentially the conservation of energy momentum tensor. You immediately see the same identity expression. You get A plus B equals to 0, C plus D equals to 0, and B plus C plus F equals to 0. The same expression which was there in your previous slide. Okay. So now, once you have linearized the action, once you have written down the linearized equation of motion, then what you have to do is that you have to invert that equation of motion to find the propagator. And of course, the finding the propagator is a little bit more complicated. I'm not going to go through all the computation because it's not very hard. Anyone can do this simple exercise, but let me skip that. And at the end of the day, you get exactly similar transverse traceless part of the propagator, the longitudinal part of the propagator, and the traceless part of the propagator. And so this is again similar to your normal GR. What you get now, this tensorial part, the spin 2 part, but now it has A of box. So these A, C which you see, they are function of boxes, means function of essentially these higher derivatives. So just to remind you that your A, B, C are essentially your these F1, F2, F3, the function of boxes. Okay. So you get similar kind of structure, 1 over k square, and for the scalar component again you get A minus 3c k square, and this part essentially this is the part which is the vector part essentially, that actually you can see from the Bianchi identity itself, it decouples, because you can take f to be 0, and it in this particular gravity it happens because if you take f to be 0, because I said that f is redundant, so I can switch it off, I can make it to 0, then I'm left with the quantity c minus a. But now you see, if I write down this propagator, you will see that, so let me write down in the corner somewhere here, this propagator, because then we can discuss. So this is the propagator, and pi equals to P2 AK square plus P0 S A minus 3C K square plus PW 0 component C minus A plus F K square. And I have, from the Bianchi identity, I had A plus B equals to 0, C plus D equals to 0, and B plus C plus F equals to 0. So this is the propagator I get from this modified gravity. But, so P2 is the spin 2. Transverse traceless part. And this is, I think, the T part. This is the scalar. Trace part. And this is, I think, the longitudinal part. Yeah.
It's not trace, it's not transverse. It's just the traceless part.
Sorry, you're correct. It is a traceless part, and then there is a transverse. This is.
There is a trace. The scalar is just the trace.
This is the traceless part. P0. This is the scalar part of the propagator.
The trace.
Yeah. And P2 is that. Yeah.
Now you seem to be different.
You have no. You have this part again, P2. You have P0 part, but you have on top of that extra state, which is this.
Vector belongs to spin 2.
No, okay. So this is okay. So there are, if you recall, there are 4 projection operator. Okay, I don't. On top of that, even I don't recall because it's slightly complicated. But there are 2 spin components which 2 spin 0 component which kind of like match. Which couple to each other. So it's one of the spin 0 component, one of the scalar part which is I have defined as W. But anyway, for the purpose of this talk, it will not matter, as I will show you why. Okay, so this is the kind of propagator which you get from modifying this action. But at the end of the day, so this is say, let's say 1 or modified MOD, and this is your GR. And the GR, let's write down here so that we can compare it. So this is the GR part. In the IR, I need to recover my GR propagator. Yeah? If I need to recover my GR propagator, I immediately see that there is a constraint here. And this will further simplify the action in a way, which Kirill has already pointed out. So in order to recover from this to GR, I need to impose A has to be equals to C. Then only I get this 1 minus 3, which is minus 2. Yeah? Now, as soon as I make A equals to C, this goes away. But as I said that I still had one redundancy, which was your F3 is R mu lambda sigma term, this last term. And I said that F3 is redundant around Minkowski. So essentially I can switch F to be 0. So if I do that, essentially this degree of freedom does not propagate anymore. I decouple this degree of freedom completely from my rest of my degrees of freedom. Sure.
In the stainless case, which term does it correspond to? The ghost in stellar.
Oh, ghost in stellar, it's completely different. We have gone beyond stellars, but I will answer that question maybe towards the end of the talk. I can come back to it, that which part of the Kelly stellars. To answer it very quickly, the spin 2 part has a ghost in the Kelly's case. So we have gone a little bit beyond Kelly's domain essentially. So this component essentially goes away. So if I have a different pen, you see that. So I am left with only this part of the propagator. Okay, but still I have one modification which I am left, and if I write down that maybe here, so I am the final modified propagator will have P2 case AK square minus P0 2 AK square. I still have A, which is essentially function of case, because A initially had this infinite derivatives of terms, like here. Yeah. So if that's the case, you see that this theory is still not good, because I have one degree of freedom which can be hidden in this A. So I need to specify this. Yeah. I need to specify this because even at this level, I can have any. A of k could be anything. If A of k could be anything, in the sense like say k to the k, if A of k is, let's say, just to give you an example, k square plus m square, I would immediately see that the residue is, again, I can decompose my propagator, and I would see immediately the residue has ghost. A of k, yeah, here I cannot do it, but from here it should be easy to figure out. Actually I have the next slide. I have a next slide to compare with the Kelly's case, and I will show you exactly with the fourth derivative gravity. So in the fourth derivative gravity, your propagator looks like 1 over k square times k square minus m square. So this is the question which you were asking. From ABC it will be a little bit complicated because I have, yeah. I mean, you can do it, one can do it. Yeah, one can do it, it's just one has to sit down a little bit because many of these terms are not there in Kelly's case. So the mapping is, there, but one has to be a little bit careful. Yeah, you have to. Exactly, you have to switch off many of the terms from these terms. Not all the terms are present in the Kelly's case. Yeah. Okay, so sorry, let me go back to one step further back. So essentially, it tells me. So essentially, my propagator dictates. My propagator tells me what I need to do. I don't want any extra state. What I mean is that I don't want any new state which is propagating other than my massless graviton, because this is the massless graviton, the one which I had written down. 1 over k square. This is the GR propagator. So this is the massless graviton propagator. So this I want to preserve. So if I want to preserve this one, then at low energies, it has to go to 1, k tending to 0. Essentially it should be k square because these are box. Box has 2 derivatives. So this is the condition I need to impose if I want to go from this propagator to this propagator in the infrared. But in the UV, you can ask the question, what kind of modification do I need such that it does not introduce any other extra state? So in order to do that, you see that these A comes in your denominator. Yeah? So in your denominator, if it comes, then it means it can give you extra pole. So you want a state, or you want a function which does not introduce any other extra pole. Yeah? So what kind of function would you like to have? Now, one particular function in branch of mathematics which is very popular is called entire function. Because entire function has this very interesting property that it doesn't introduce any other pole from here to infinity. If you look at the infinite domain in a complex space, complex plane, then the only singularities which it will give you only at the boundaries, but not intermediate. Okay? So that's the kind of function which you would like to have, because you do not want to introduce any other extra state which is propagating. So that these two conditions tell me that A of k has to be some kind of like an entire function. But there are many, many entire functions. So the question, what kind of entire function should I choose? Yeah. So of course I need to choose my entire function cleverly, because at the end of the day I need to satisfy my boundary condition. Because in the infrared I need to get this to be 1 to match my pure GR propagator. So one example, it's not exhaustive, but just one example I'm giving you, which could be your e to the power minus box square over some cutoff, because this has a scale, yeah, m square. So this is one example, because when I go into the momentum space, this becomes k square. When k goes to 0, it's essentially 1. So I recover my pure normal GR propagator. So let's ask the question, if I take this e to the power, this form of entire function, what can I say? What can I do to my rest of my problems? Okay? So let's entertain this fact. So let me come back to the Kelly's case a little bit further. Later on I can come back.
Is there a reason for choosing the minus sign in the expression?
Okay. So is there okay. Why did I choose minus sign? Because I want just to keep it. Okay, so because you have 1 over a box, yeah, 1 over k square minus 1 over 2k square, yeah. So a of box you are taking e to the power minus box over m square. Okay, so that's what I need to make sure that at the end of the day it satisfies this. And in the UV, in the UV I want to mellow it down. I want to soften it. So you will see why the negative term plays a role. Because in the UV I want to resolve the singularity issues. So you will see why I do that. Yeah.
It's strange because so you expect the larger energies.
Hmm?
They only become larger.
I want to make it soft, so that I want my gravity not to propagate in the UV. So I want to really, take away gravity essentially as a dynamical degree of freedom. I want to freeze that aspect. Yeah.
You said that A in the numerator, in the denominator,
Yeah.
E to the minus something.
Yeah.
Denominator,
Yeah.
same as E to plus something.
In the numerator, yeah.
So the propagator blows up high energies.
Propagator blows up at high energies. Wait a minute. Why? Let it. Yeah. So okay. So you are saying is that what you are saying is that if I take this to be minus box square over m square, in the numerator it blows away. That's what you're asking. Okay. Yeah. That's fine. In the numerator it will blow away. Essentially, in the numerator it will go as box over m square. But when you do a Fourier transformation, you will get minus k square. So that's why I mean the confusion is because I'm writing down in terms of box and k. So it is my mistake. So when you do a Fourier transformation, for every box you get essentially minus k square. So at the end of the day you want to soften the behavior. good that you asked me this question because it got clarified. Okay. So where are we? So yeah, so this is the kind of propagator you get at the end of the day, and once you get this, once you impose this A equals to C, okay, it actually starts putting constraint on my functions f1, f2s, and f3s. So this alone starts putting constraints, and as we said that f3 is redundant, so essentially you are left with these two functions, 2f1 plus f2 is 0. Okay. Okay, so now let's ask the question. So once we have determined the form of f1s and f2s by simple analysis, so we have a relationship between f1 and f2s. So at the end of the day, you are dealing with only one uncertainty, which is essentially this A of box, which is encoded in terms of f1s or f2s. Okay. Okay. So this action further reduces, and as you said, that you are left with only these terms to play around. So now, what are the applications can we discuss? So two of the applications which are very interesting for every one of us sitting here is what happens to, let's look at the black hole singularity, and let's look at the cosmological singularity.
Sorry, where does the 1 over box piece come from?
Sorry, could you repeat it?
Where does this 1 over box come from?
Oh, 1 over box, okay, I see. So 1 over box essentially comes because you have this, you have chosen this form of A and C, yeah? And mind this expression, if I go a couple of slides before, yeah. Sorry, I went quickly. You see, A is 1 minus, C is 1 plus, so this one factor comes essentially by playing with these expressions.
It's multiplied by box.
Yeah.
So we need 1 over box.
Yeah,
So if you expand this method,
exactly.
powers of the box,
Absolutely.
cancel away.
Yeah, so that's very simple answer essentially, what Kirill has said. Okay, so let's look at some of the simple applications. So let's look at the black hole, simple solution like black hole. Now we have to keep in mind that, look, I mean, what I have done is that I have, to be honest, I have solved a very, very simple problem. I have not solved anything significant here. What I have done is that I have found the equation of motion around a Minkowski background. So that's the only thing which we have done so far in this talk, nothing beyond that. Okay, so if I have done something very simple, the only place where I can apply this, where my perturbations are very, very small. Yeah, so very small perturbations around the Minkowski space. That's what we are talking about. We are not talking about astrophysical black holes. We are talking about very, very tiny system where the it is perturbing around the Minkowski background. Astrophysical systems near the horizon, they are no longer. I mean, you cannot describe them in a linear theory. You require the full action and full solution, which we are not doing. So let's. So if this is what we were doing, so let's stick to that because that's what our approximations are so far valid. So here you have this two metric phi and psi, and everyone knows when you perturb it around the Minkowski space, you get two. Essentially, you can rewrite everything in terms of these two Newtonian potentials, phi and psi. Now, in principle, phi and psi need not be equal. Okay, they can be very different. But so let's study both these Newtonian potentials. So you know the equations of motion. You add a source term. So anyone who solves the black hole problem has to realize that you need to put a source term. Otherwise, you don't really get a solution. So the source term here is kappa times rho, where kappa is your usual Newtonian constant. Okay. So when you do that in the linearized limit, you can rewrite the expression because it's a. Let's consider a very simple problem. Even forget even the black hole right now. Let's consider a simple problem where yeah, I raise this part. Can I raise it? Oh, I like this kind of boards. This is fantastic. Which you can raise. I didn't realize it. So okay, so let's consider a very simple problem, exactly what you would do like a Newtonian potential. Suppose you have two, just say 1 point source, rho, okay, delta source, delta function, just sitting at 1 point. You want to understand what's the Newtonian potential. That's the simplest zeroth order problem which you can ask. How does it really recover your usual Einstein's Newtonian potential at the end of the day? So the problem simplifies a lot. because you assume that this source is moving very slowly. For a slowly moving function, this box is just modified. There's no time dependence, there's only spatial dependence. So you reduce the problem a lot. And when you reduce the problem, at the end of the day, this is what you get. Some number A of box, or A of k square, if you like, del square, because now you have only spatial derivatives, no temporal derivatives. Phi equals to A del square psi. The potentials are same. Some kappa times your point source rho.
You get potentials to the same
Exactly.
mathematically, or
No, I don't impose. It comes from the equations of motion. Okay. So this is the problem which you have to solve, and everyone has solved this problem. This is nothing but the Gauss problem in your electrodynamics or your Newtonian potential, besides, except this factor. Yeah. So it's very simple to solve it. You solve it analytically, and at the end of the day, what you find is this expression. You see, this you will recognize. So when you look at the potential, phi equals to psi, guess G, your usual Newtonian constant. Suppose you put the rho to be m, essentially the scale, the mass scale, yeah, gm over r. But on top of that, what you get an error function, which is given as r times m over 2. Now, what is this capital M? The capital M is the scale, because as soon as you have done this high derivative expansion, as soon as you're writing down your action in terms of boxes, box square, and box cube, there is an inherent scale sitting here, yeah, m square, m4. Now this scale, you can take that to be m Planck, or you can take that to be some intermediate scale or string scale, whatever you like. But let's take that to be m Planck, just to simplify our life. So I fix only one scale, which is my m Planck, the usual Planck constant. So then you see that Newtonian potential turns out to be like this. Okay, you plug that in your metric, what you get is your simple expression. Yeah. Now, this is what I've done. I've just plugged the solution back into my metric, but the error function has some interesting property. Now, this is what I have plotted here. Now, error function, when r tends to infinity, the error function becomes 1. So if the error function becomes 1, at the end of the day, you recover your pure Newtonian potential with the minus sign. Yeah, there has to be minus sign, minus gm over r. You recover the usual Newtonian potential. This means that in the infrared, you recover your Einstein's gravity, you recover your Newtonian gravity. So that shows that, okay, at least you have some confidence, you can understand this theory a little bit better in the UV. And in the UV, what happens? The same error function, when r tends to, when r goes to 0, essentially, r tends to essentially 0, that error function goes as r. So error function has the property, if you remember, when r tends to 0, it approaches linearly. When r tends to infinity, it goes to 1. So when you look at these two limits, you find that essentially the blue line, you would expect from the pure Newtonian gravity or pure Einsteinian gravity, your function would keep blowing up. But here, instead of blowing up, it's just a cartoon picture. What it does is that it caps. It's no longer blowing at r equals to 0. It has some finite value. And you can compute that finite value. The finite value will come around this number, m times m. And if I fix that m to be m Planck, then what it tells me that my linearization works if the mass of my system, which is sitting here, is much, much smaller than m Planck. And keep in mind that 1 m Planck is roughly 1 part in 10 raised to 5 grams. So the system which I'm talking about in physical terms is much, much smaller, very tiny mass. Mass smaller than 1 part in 10 raised to 5 grams. I put the function directly. Oh, what I'm plotting here? I'm plotting the Newtonian potential. So Newtonian potential with respect to r. So in usual and Einstein's gravity or Newtonian gravity, my potential would blow up at r tends to 0. But here in this expression, as r tends to 0, it's no longer blowing up, but it has. Ah, that's true. That's you are, yes. Of course you are, yeah. As Kirill pointed out, what is happening here in this case, I mean, of course, he's much more experienced, so you could see that he can immediately figure out that this has no horizon. It's not crossing the 0. because essentially in this particular case it is not happening. Oh, I can move it further. I like it because phi and psi both are less than 1. So 1 minus 2 phi dt square 1 minus 2 psi, 1 plus 2 psi dr square, where these terms are always less than 1. So in this respect they are never crossing the so there is no horizon, they remain always less than 1. Yes, that's what you get. So here there are two things which you are getting. For small, of course this will not hold for massive black holes. For our within this approximation that m is much smaller than m Planck, what is happening, you are getting two things. One is you are smoothing this behavior of the singularity, and also this is your metric ds square, and also this metric doesn't have any horizon. It doesn't cross. Yeah.
The special part of this metric is only valid linearly, so it's basically 1 plus 2, 3.
Yeah. Because it's a small quantity, exactly. It's a small quantity. You are expanding around the small number. Yeah, that's true. But it will not hold. For your intuition is absolutely correct. If I had solved this problem full-fledged, full nonlinear equation, the horizon would still be there. But it is just the property of, because I'm doing it at a very small perturbation, that's why the horizon is not there. But in a way, it sheds some light for the information loss paradox also. One of the reasons this Hawking's paradox is essentially the entangled state. One state which goes inside the horizon, the other state which comes out. So you are never getting a pure state. You are getting always an entangled state. But at the end of the day, if the end product of a black hole doesn't have this horizon, at the end of the day there is no information loss. Because at the end of the day you wait billion years from now, maybe you will recover the other state. So there is no longer you have to wait, the entangled state anymore. So that's something which okay, it goes slightly beyond my today's talk, but it has the potential to shed some light in this direction. Yes. Okay, so it's good that you have pointed out. Let me summarize. The similar way you can actually resolve the gravitational waves also, because gravitational waves exactly behave similar to your the one we discussed. You can resolve the singularity close to the source. So let me go very quickly now. But with the same same constraints, one can also resolve the cosmological part. I didn't have much time to discuss. One of the solutions which you get a sinusoidal solution. For pure Einsteinian gravity, it's never a solution. But for this action, you get a sinusoidal behavior, which tells you that universe has this bouncing kind of behavior. And I'm skipping quite a lot of details here, but we can discuss once after the talk. We can go ahead and discuss. So let me close the discussion that there are two aspects which you can work on it. One can take this action as just an action and ask various kind of questions. Classically, you can ask the question, what happens to a much bigger problem like singularity problems and things like that. And on one hand, so this is a purely classical aspect of the problem, and in the quantum aspect you can ask the question, what happens on top of this? Can you write down extra corrections, 1 loop, 2 loops, 3 loops, and things like that. So these are two directions which you can work on in this side of gravity, and both of the directions are completely unknown, completely wild. It's a completely an open territory, and we are just simply working on some of the aspects of the problem. So let me now summarize my talk quickly by giving the conclusion, but I have spoken a lot, so I think it should be obvious what the conclusion is. So let me thanks to all of you for your kind attention. Yeah.
Yeah, you started from the uncertainty in Minkowski and you found some parameters, and so what would happen if I just take that theory at face value?
Yeah.
I take it as a theory.
Yeah.
And I calculate some other backgrounds, like cosmological backgrounds.
Yes. Yes.
Would I expect the unitarity to still hold? Or
No. That's a good question. Very good question. So that comes to my conjecture part, which I have not proven it yet, but sometimes when you work on a theory, sometimes you get some intuition. So I'm based on complete intuition. So don't take it as a face value. Judge it as a grain of salt. What would happen is that these terms, these coefficients which I was writing down, yeah, they were only function of r, yeah, essentially, or one parameter. Now they will get converted. They will not be some simple saying, if you want to solve the same problem in de Sitter or anti-de Sitter, yes, you can solve it. You can do the same procedure around any background. But these expressions will a little bit more complicated. So essentially what will happen is that expression which in the square brackets, they may not be simple as what I have written down. They will be more complicated functions. So that's the intuition I have. But in principle, you can do it for any different background. So it is a background dependent coefficient which you will have to write down. No single theory. No. It will be hard. It will be hard. That's what just from my intuition, again, because I have not proven it, from my intuition it looks like that these coefficients will not be single number. But that's the beauty of Einstein's gravity, that he was genius because he wrote down one term, it holds so well for the IR. Yes, please.
Why is it enough to have A going to 1 only in the limit? I mean, as soon as you have a little k, that's you wouldn't propagate modes or...
No, you are propagating. Of course, this is a limit in order to recover your infrared part. Of course, when this is away from 1, you are modifying your essentially the propagator.
Why is it enough to just have it in the limit?
Oh, okay, yeah. So the answer is essentially here. So when I plotted the Newtonian potential, you see that you see the departure. So now you can ask interesting question: at what scale do you see the small departures from the Newtonian potential? And people are doing. You see, sorry, yeah. You can see that. You see that there is a when you approach R very close to the source, you would see a departure, and those departures are being captured by essentially going away from 1.
Yes, sure, but does it not correspond to propagating?
Oh, no, it doesn't, yeah. So although these, that's the reason, that no matter, because you are capturing this by an entire function, an entire function does not involve any singularity, any pole. So you are not introducing any extra pole, you are just playing with the massless graviton. But you are modifying the massless graviton in such a way that in the UV, it mellows down the property, and in the IR, it recovers your pure IC. Yes, exactly. Yes. Sure.
About the initial conditions, if you have any number of derivatives in your equations of motion, do you not have to pose basically infinitely many initial data?
That's a very good question. Yes. If you want to solve the problem, full-fledged problem. Suppose I had to solve this full nonlinear problem, I would have to impose infinite number of initial condition on my given surface. Now, so that's the problem. However, as you can see, that in spite of all these problems, when its equation of motion, when you can write down, when its equation of motion becomes of second order, which is actually for the linearized case, the equations of motion will become del square phi, del square psi. So then that problem ameliorates. But if I had to solve the full-fledged black hole solution, I would come across to the same problem as you have said. So there are problems, of course, with these kind of issues. They're technical problems.
Because your propagator just has precisely this structure.
It has precisely this structure.
It's just
That is true essentially around the Minkowski background, but in general it may not hold. In general it may not hold, exactly. So in general, I mean, what I have said so far, you have to again keep in mind, I have done everything around the Minkowski background. I have not done anything beyond. So once I open up my problem a little bit more, I will have to face all these issues. But okay, even in so this, you make a start. So this is the 0th order problem, and this is what you have got. Gradually, you will make progress. So the two directions which I'm right now concentrating on is looking at the one loop corrections, and the other aspect is to look at making some non-perturbative statements, such as what happens to the singularity theorems, like looking at the Ray-Chaudhuri's equation, which are based on that, essentially Hawking and Penrose proved that all the singularity theorems. So some of these things one can study this direction. But it has many interesting avenues, as you can see, just propped up from the discussion. So.
Can you actually address singularity theorems with the first order perturbation theory?
No, I don't have to do any perturbation. I can there I cannot do perturbation theory. I have to take the full action. I have to write down the essentially the analog of Ray-Chaudhury's equation, and then ask the question: what happens to the null rays in this?
Full action. Which action?
Okay, so the full action will be essentially, let's say, the full action which I need to work on would be essentially the top action. I would take this top action, okay, and then I will ask the question: what happens to the two null rays, and whether they really meet based on my strong energy conditions. I do not want to violate my strong energy condition. Rho has to be greater than 0, rho plus p has to be greater than or equal to 0. So strong energy condition, weak energy condition has to be satisfied, and still show that somehow these two rays, they don't meet, but somehow they bounces back. If I can show that, then it will give me again it's a very powerful theorem, because it will tell me that maybe I do not form singularity. Of course, it's not a proof, it's not an evidence, but it's kind of like it gives you a hint. So in order to prove it, you really have to solve the full-fledged equation, solve the black hole kind of solution, and prove it. But of course, as you can see, it's not so easy. Yeah.
Why it sounds like you take this theory, this particular theory, seriously.
Okay.
As this discussion showed, as you admit, this theory will have ghosts if you expand it around different background. So it actually secretly has more degrees of freedom. You just don't see degrees of freedom in the linear theory.
Okay, that's a good point. But you see, the black hole, even for astrophysical black hole, is something interesting, because astrophysical, suppose there is a black hole sitting in the center of my galaxy, and I am an observer, want to study this problem from Earth. For me, the metric is actually linearized. It's a very small perturbation. So for a very far away observer,
You're taking this seriously as a nonlinear theory.
yeah. So I mean, in a way, I can take it. Sorry? No one has, I have shown, okay, so what I have shown, that this theory has non-ghosts. That's what I have shown around the Minkowski space. So as long as I stick to the, that's true, along the linearized background, it is true. Now, as I said, that maybe in the true, so I do not know what will happen to really astrophysical black hole, because I have not really solved that problem. But still, even in Einstein's gravity, you are in a Minkowski space if you put a source. So the beauty about this calculation is that you have a source term, delta Dirac source term, okay? The source itself has an infinite energy density, but still it gives me a finite answer. And that finite answer comes from the fact that my potential does not blow up. You see?
This is a linearized thing.
It's a linearized statement, I agree.
It's a linearized statement.
Yeah.
It sounds like you take this theory seriously.
That's one step. Of course, it's an ambitious game. I'm not saying that it will.